In the last video, we started following our intuition to develop the concept of torque, which describes how forces attempt to rotate an object. To that end, we will have to work towards developing a concept of angular acceleration so that we can connect the dots between the torque and the final output of the rotation. To get there in between, I'd like to make a detour on thinking a bit more about how it is that things know how to rotate. So to this end, we want to take a look at the rigid body model. And I will start by shooting it down, but then deciding that maybe it wasn't so bad after all. In the rigid body model, what we do is we say that as an object rotates, it if it's a rigid object, it doesn't change its shape. Now let's think about that for a second and just ask ourselves, how true is that? So what I've got drawn here is a bike wheel, and I drew in 4 hole spokes. And let's say it's rotating counterclockwise like so. All right, now I've highlighted a section of the bike wheel at the end of the rim here, so the tire and the rim together, where a spoke attaches it. So what I want you to think about is to ask yourself, how is it that that chunk of wheel knows how to go around in a circle around the middle of the bike wheel? What forces are making that happen? Pause and get back with me on that. Okay, so hopefully upon reflection, what you realized is that in the first instance, it doesn't know. What that chunk of the bike wheel is going to want to do is, by Newton's first law of motion, is just move in a straight line at a constant speed. But now let's think about what that means for the spoke. For the spoke, that means that since this chunk of mass is moving forward and it's attached to the spoke actually has to get stretched out just a little bit. So if I go and notate a slightly later position after we start rotating, the bike wheel chunk has moved straight forward, and our spoke has gotten just the tiny, there we go, I guess we'll have to do that. Doggone it. There we go. And our spoke has gotten just the tiniest bit longer. So that means that since the spoke is stretched, it's going to want to return back to its original shape. And in so doing, that spoke is exerting a force due to tension. Let's see if we can draw a little better. There we go. A force due to tension directed into the center of the spoke, into the hub. And so this way, that chunk of bike wheel knows how to move around the hub in a circle. Now let's take this a little further. Let's say you're mashing down on the pedals of your bike and you're picking up speed. In order for the wheel to spin faster, the chunk of that chunk of tire would also have to somehow know how to move faster. How do you suppose it figures that one out? Again, think about that for a bit, pause the video, and get back with me. Okay, it's the same deal. Literally, it doesn't. When you mash down on the wheel, what's going to happen to your spoke is that instead of your spoke being a nice straight line, oops, say like so. Let's try that again. There we go. So it'd be a nice straight line like so. When you start mashing down, what's going to happen is you're going to, because this bit up here kind of hasn't gotten the memo yet, you're actually going to deform the spoke into a bit of a curve. And the spoke is going to want to return back to its original shape. And so as a result, it will exert a tangential force on the chunk of the bike rim in order to make the bike rim speed up. So all of this is to say that there is no rotation without deformation. In order for anything to rotate, even if you're just rotating at constant speed, the bike wheel got microscopically bigger in order for all the spokes to get longer. Or we could have the spokes no longer being straight, in the case of mashing on the pedals to pick up speed. But in any event, if things are rotating, they are getting deformed. So in an extreme situation, say if you're a company designing bike wheels for elite cyclists, you may just plain have to have computers very carefully analyze what collections of molecules within the wheel would do, what's called finite element analysis. But for you and me, since we're not worried about making the bike wheel as light as possible and having some of the world's most elite athletes mash on the pedals, the bikes you and I ride are much more over-engineered, have way more spokes in them than would be minimally necessary, and we're probably not going to be mashing down on the pedals as hard as, say, some elite cyclist working their way up one of the Alps in the Tour de France or something like that. So in that case, although yes, our bike wheels are deforming too, they're not deforming anywhere near so much as in the case of an elite cyclist really hammering it in a competition. And so for us, even though the deformation is happening, it can be very computationally convenient to pretend it doesn't. So the rigid body model is when we say that the object is, we acknowledge in our heart of hearts that the object is deforming, but we say that the deformation is so small that we can get away with pretending that it doesn't happen at all, and the errors that we make will be very tiny. So if we can make such an assumption, and a lot of the times we can, there are cases where we can't. For instance, modeling the sun's rotation. The sun's a big ball of hot plasma. That doesn't work out so good. But in many circumstances, it turns out that we can get away with this approximation very accurately. And so a result that comes out of that that's beyond the scope of this class to prove, but I've stated it before, is that, say if you go and take your pencil and just give it a toss off at one end, you'll see it both move and spin. And this is going to go very badly with me attempting to draw it. So here's your pencil, and then maybe if you put some backspin on it, maybe it's doing something like that. There's a key result of the rigid body model that says that if an object is rigid, when we look at this, we can completely describe this as the translation of the center of mass. If you were to find a point on your pencil where it balances on your finger, and you were to mark that in some other color and do this, as you toss it, you'll see that that colored mark will just move in a parabola. So we can talk about the translation of the center of mass and say that, yeah, it's moving in a parabola. And then we combine that with its rotation about its center of mass. And that's it. So if rigid body applies, we can treat as translation of the center of mass. And we'll define center of mass better later. But for now, just the point at which, say, your pencil would balance or whatever, plus rotation about center of mass. Now, to be clear, when we're thinking about our bike wheel rotating, we're perfectly free to use nothing but Newton's second law of motion. It's just that when we start thinking about how the spoke deforms, we're having to do more of a molecule by molecule kind of analysis using Newton's second law, and that might get a little tedious. This result allows us, instead of having to think about the x, y, and z components of motion for every single molecule, gets us down to at most 6, and in practice really usually just 3 variables that we have to keep straight. So that versus 10 to the 23rd variables to keep track of. This is a very handy result to have indeed. So with all of that, that means we need to do a little more about talking about the rotation about the center of mass. In the past, we have already defined angular position. Theta. This is the angle that something has turned from some reference line, and keep in mind it keeps a turn counter, so pi and 3 pi aren't the same thing. And we already saw angular velocity, which is the time rate of change of the angular position. And so you might guess where we're going with defining angular acceleration. It is the time rate of change of the angular velocity. Now this little squiggle here, which I drew kind of badly, is a lowercase Greek letter alpha. So going back to the special paper that we all used in about 3rd grade, you would draw one like that. Resist as much as possible the temptation to turn it into a cute little fishy. Apparently I failed. All right. Oops. Come on. Doggone it. Stop it. There we go. All right, so what does this tell us? Well, first let's look at the units. Since the units of angular velocity of angular position was radians and angular velocity was radians per second, this is indeed radians per second, or radians per second squared. And again, just a reminder, technically a radian is not a unit. It's just a symbol that we use to remind ourselves that we're working with an angular quantity. And when we balance our units, we just replace all of our radian symbols with the number 1. And as long as it balances, it's okay. We don't have to have the same number of powers of radians on one side as another. So how do we interpret the angular acceleration signs? So for positive, the way I interpret this is to say that the angular velocity is becoming more counterclockwise. So there are two ways this could go. One way would be if I'm already turning counterclockwise, and then I turn counterclockwise faster. Another way, though, would be if I were turning clockwise, which would be a negative angular velocity, and I end up turning clockwise slower, so a less negative number. That means that the angular velocity would be becoming more positive, which means that the angular velocity would be becoming more counterclockwise. Alrighty. And similarly for the minus sign. If the sign of angular acceleration is negative, that means the angular velocity is becoming more clockwise. So again, this could go one of two ways. We could either be already rotating clockwise, omega negative, and then I could be going clockwise even faster, so omega even more negative, or I could be going counterclockwise, so omega positive, but be slowing down on that, so a smaller positive number. So that means that omega would be becoming more negative. Now, we had already seen a relationship between the component of acceleration, of linear acceleration for an object directed toward the center, and omega. And now we are in a position to handle the tangential component. So let's say I'm swinging a stopper around in a circle tied to a string, or we can tie a ball to a string, whatever. It's going around in a circle. And let's say it's speeding up. If it's speeding up, the string will actually be pointing, sorry, I'm terrible at drawing hands here. Yeah, I'm not even going to try. The string will actually be pointing ahead of center. And it has to, because much like with the bike spoke issue, we need a component of the tension directed tangential to the motion in order to make it speed up. So this also means that the acceleration is directed ahead of center as well. And we can break that into our radial or centripetal portion and our tangential portion. And we've already seen before that this was r omega squared. So now let's work on the tangential piece. The tangential piece of the acceleration is responsible for changing the speed. It's like the centripetal piece is responsible for changing direction. The tangential piece is responsible for changing speed. So its magnitude will be equal to the time rate of change of the tangential velocity, or the speed of the object. We've already seen the tangential velocity was equal to r times omega. But under the rigid body assumption, r is a constant. And so the change in r times omega is the same thing as r times the change in omega. Oh hey, delta omega over delta t, that's the angular acceleration. So you've seen the centripetal component of the acceleration is r omega squared. The tangential component is r alpha. So where does this lead us? Well, it turns out that we are now free to do rotational kinematics. So again, the key assumption here is that alpha is a constant. So under that assumption, it turns out that since angular velocity and angular position have the same kind of mathematical relationship with each other that linear velocity did with linear position, and translational acceleration and translational velocity have the same kind of mathematical relationship between each other that angular acceleration and angular velocity do. Although these angular quantities are different physical quantities, because the underlying mathematical relations are the same, if you make the same kind of assumption, angular acceleration being a constant, you wind up getting a whole new gang of 4 kinematics relations. And so I'll just go ahead and write them down here. We'll have that omega final equals omega initial plus alpha t. So here you're missing theta. And then we can have theta final equals theta initial plus omega initial t plus 1/2 alpha t squared. And we'd be missing omega final. We can have theta final equals theta initial plus 1/2 omega initial plus omega final times the time. That would be missing alpha. And finally, we have omega final squared equals omega initial squared plus 2 alpha theta final minus theta initial. That one's missing the time. So if you've got a situation with constant angular acceleration, you can go to the same sort of toolbox you did before. Again, these are different physical quantities. But you can go to the same sort of toolbox that you were going to before, and you can figure out a different one of the kinematic variables using the same kind of trick of identifying the missing variable. So let's just try this as an example real quick here. Let's say you got a merry-go-round. There we go. And we will say that initially its period is 4 seconds. And we know that it slows down to a stop at 20 seconds. So it uniformly slows to a stop. What I'd like to know is how many revolutions does it make coming, to a stop. Okay, so what's that really asking for? Well, if we say theta initial is 0, this is asking for what is theta final. So, all right. We at first might not think that we have omega initial, but actually we do. Since we know that it takes 4 seconds to turn a revolution, right? Omega initial, that means it would be turning through 2 pi radians in those 4 seconds. So we can work out that's pi over 2 rad per second. So okay, we know omega initial, we know omega final, we know t. We're being asked for theta. So we are missing alpha. So we go ahead and write down our missing alpha equation. Theta final equals theta initial plus 1/2 omega initial plus omega final times t. Omega final is 0. Theta initial is 0. Okay. So our angle will be pi over 2 radians per second. Sorry, 1/2 times pi over 2 radians per second times 20 seconds. Okay, cancel, cancel. So we're up to 5 pi radians, but they asked for revolutions. So we'll have to unit convert that. And remember, there's 2 pi rad in 1 revolution. So, hey, we lose the pi's. We have 5 halves, so 2.5 revolutions until it slows down and comes to a stop. Okay, in the next video we will be introducing Newton's second law applied to rotations and develop the concept of moment of inertia. Have a good one.